So in the last class, we had started designing the PDA. So I'll continue from there itself. Okay, we'll solve some 4 problems today. If you have doubts anywhere in between, please let me know so that I can explain it once more. So in case you have forgotten, PDA is push down automata. So what is the difference between all other automatas that you have studied so far and push down automata? The difference is that in push down automata, we make use of a stack, correct? We make use of a stack. So otherwise, other other attributes means when you design a machine, you will have tuples, right? So K, sigma, tau, delta, S, and A. This S is small letter. So out of this, you already know K is states. This is same like other machines. So sigma is alphabets. So this also you have studied in other thing. Delta is transition functions. So transitions you studied with names like delta or R, rules so far, correct? And S is the small s, that is starting symbol. And A is a set of accepting states. So all this you have been studying from before, right? They remain common, correct? So what is different then? The different symbol is tau, and tau is stack symbols, which means when you designed a PDA, what can go inside stacks, you are determining them. So those are the stack symbols. Okay. So the first problem that we started with in the last class was design a PDA for a power n, b power n, which has strings small a power n, b power n, where n is greater than or equal to 0. So we had to design a PDA for this. We did design it, but I'll again repeat it so that we can move ahead slowly with the then if you understand this properly, other things are easier for you to understand. That's why. So whenever they say design, please never forget that you have to write about everything. That is, you have to write what are K, right? And what is your sigma, what is tau, what is delta, and which is the starting symbol, and what are the accepting states. You have to write all of them. Whether I explain them in for each problems or not, you have to write all of them. Okay. For first problem, I'll explain, and for remaining, you will have to write it by yourself. Okay. So this we already designed in the last class. So as you can see, n is greater than or equal to 0, which means when nothing is there also it should accept. So whenever a question like that comes, your starting state also becomes a final state. Okay, your starting state also becomes a final state. Now next, when A comes, so the logic we are going to follow for this, okay, the logic that we are going to follow for this is whenever A comes, this will differ for each question, right? Whenever A comes, we are going to push it into the stack. Okay. So that means whenever A comes, push it into the stack means tau will have A, correct? Because we are pushing it into the stack. And whenever a B comes, whenever there is a B in you, whenever B is your input symbol, then for each B, you pop A from stack. All right, from stack. And also you should remember that when do we accept a string, right? For example, you are to accept this equal number of A's and B's, but you should not accept this because here all B's are not following A's, right? You should not accept this. So this should be accepted, these to be rejected. So when do we accept? Okay, we accept in 3 cases, correct? We accept it in 3 cases. So when do we accept a string or a configuration? First thing is whole input string should be consumed. Okay. Consumed means you should see through the entire input string. Okay. Then what is the second condition? The second condition is you should be in accepting state. When you reach the final thing, when all input is consumed, you should be in final state. Not only these two, the third condition says that you also should be having nothing inside the stack, right? So stack should be empty. So these three conditions have to be satisfied. Okay. So now let us write the transitions. This is nothing but a delta, correct? So you are at S, you are at the starting place. Now, as I said, if you get A, what you have to do, you have to push it, right? So we show it like this, no? A, epsilon, A. This means your input symbol is A. Your input symbol is A. There is nothing inside the if nothing is there inside the stack, you push it into the stack. Okay. And on getting a B, I am making a change of state. The reason is once I get B, after that A should not come. See, this case we should reject because after getting a B, you are getting a A. The question says n number of A's followed by n number of B's. So there should not be a scope to get an A after you get a B. That should not be accepted. For that reason, we can make a transition on B. Okay. So while doing the transition, what else do we do? If I get an input symbol which is B, okay, and I have A in the stack, I am going to pop it. Okay, I am going to pop it. All right. So this representation will tell us if you have A in the input, listen to me carefully. The first one is input always. Okay. And this is what is there inside the stack. And if I put this means we'll pop. Okay. And here you remember when I put epsilon here, it tells that it doesn't mean stack should be empty. It means that doesn't matter what is there in the stack. It could be empty or there might be an A already in the stack. Doesn't matter what are stack contents. Okay. So epsilon represents both empty stack as well as something could be there in the stack. And when I put this is pushing that symbol. Okay. Pushing this symbol into the stack. Okay. Once you reach B, the transition will have only B, right? You can get only B and inside stack there could be only A and you are going to pop. All right. So this is the transition function for the question that has been given. So now what is K? How many states do we have? We have S and F, correct? That's our K. What is sigma? We have in our string two alphabets A and B. What is tau? We only push A into the stack. So tau is A. What is delta? This thing. And it can also be, that's the transition diagram. Also, you can show it like a transition function. So how will I show it? So if you're in a state S and you have A and doesn't matter what is there in the stack, then you will be pushing that. Okay. And similarly, if you are in state S and you get a B as an input, right? And you have A inside the stack, then you will make a transition from S to F, right? And pop it. And next we have, if you are in a state F here, and you have B in the input symbol, A inside the stack, then you will remain in F and you are going to pop it. So we can show it like this. Okay, two representations of the same thing. So which is the starting symbol here? We have used S itself as the starting symbol. And what are accepting states? Both S as well as F are accepting states. Okay. So this is how you design a PDA for A power n and B power n. Now let us take this as well as this and see what happens. Okay. So that's called as a configuration, right? So let us see how this PDA behaves for a configuration called as AABB. If what we have designed is correct, this one should be accepted, correct? This one should be accepted. So how do I show the configuration? I'll start from the starting state. My input is AA, BB, and initially nothing is there inside the stack. Okay. Next, you see here I am in starting state. A is the symbol, input symbol, nothing is there in the stack. Do I have a transition for this? Yes. SA epsilon, I said we have to push it into the stack, right? Consume the input and push it into the stack. So I will go to S itself because S to S, right? And I have consumed one input. So remaining three are there, and stack which was empty will now have A. Will now have A. Next again see S, A and A. Okay. S, A and A can also be this, because I told you whenever we put an epsilon here, it means doesn't matter what is there in the stack. Okay. So what do we do? Push again. So this can be written as SBBAA. Okay. This is the first A, this one, and the second one pushed will take this place. Next one is S, B and A. Do I have a transition? Yes. S, B, A. I'll make a state transition to F. And I said pop, right? So we consume an input and we pop one symbol from the stack. Okay. Now do we have a transition for FBA? Of course we have a transition for FBA. It again says remain in state F but pop. Okay. So I have reached this place. So when you reach this place, you can say that the configuration AABB is accepted. How can I say it is accepted? Because F is a final state, agreed? So accepting, we have three conditions. So final state, F is a final state. That's one condition to be accepted. Input is consumed. That is second state to be condition to be accepted, and nothing is in stack. So we have reached the acceptance state. Okay. Now I'll just move and check the chat section. I want to know whether you have, let us take one more example, reject it, and then you tell me whether you understood it or not. And can I move on to the next question or not? Okay. So let us take one more configuration. AB, AB. Even though it has equal number of A's and B's, it should be rejected. Because after B, you cannot have A, correct? So let us see. I am starting from the starting state. My string is AB, AB, and nothing is there in the stack. So for SA epsilon, I have, right? SA epsilon, I have. It says that push A into stack, right? Push A into stack. So I'll remain in S. I have consumed the first symbol, so I'm left with BAB, and I have pushed A into the stack. Okay, I have pushed A into the stack. Next, SBA. So I have SBA, correct? For SBA, it says change the state to F and pop. So the remaining symbols are AB, and this BA. A has been popped, so nothing is, this A has been popped, so nothing is there in the stack. Now if you see FA epsilon, there is no transition written for FA epsilon. Okay, there is no transition. So that's why this configuration will be rejected. Okay, so the reason is you reject a transition because input is not completely consumed, or you can also say that there is no, because there is no transition for f comma a comma epsilon. Okay, f comma a comma epsilon. Now I am moving to a chat section to see whether you have understood. Okay, so can you tell me in the chat section, have you understood that question and how we solved it? So can I move ahead with the next question? Unless you answer, it's difficult for me to move ahead. So please answer. Yes? Okay, okay. All right. So I'll go back to the whiteboard. Now let us take one more question. Okay. So let's take balanced parenthesis. Okay. The question will be design PDA for balanced parenthesis. So what do you mean by a balanced parenthesis? So you already know it, right? For every open, there should be a close. So this is balanced, this is balanced, this is balanced, right? This is not balanced. It's wrong construct, correct? So this is not balanced. This is not balanced, etc. Okay. So we have to write. Okay. So let us develop the logic. What we are going to do. How we are going to design a PDA for this balanced parenthesis language. Simple, just like it's almost similar to your A power and B power n. Almost. Okay. Almost, not same. The reason here is for every open bracket, push it into the stack. Okay. And for every closed bracket, pop from stack. Why I said it's not exactly similar is because in this case, once you got B, you cannot get A. But here it is not like that. No, after closed bracket also you can get a open bracket again. Right? After this closed, you are getting open bracket again. So that's why it's slightly different. Okay. But otherwise, we are going to push. Right? Push whenever you get a open parenthesis and pop whenever you get a closed parenthesis. So let us design it. Okay. So it's very simple. Let us be in starting state and also make it as a ending state, because the question has star. Oh, I didn't write the question at all. So the question is like balanced parenthesis will have all those strings which are derived from two alphabets. Star. Star means if nothing is there also, then parentheses are balanced, correct? The parentheses are balanced. This is actually question. Okay. So what did I say? So I said if you are in a starting state, whenever you get an open bracket, doesn't matter what is there inside the stack, push it. That's one transition. And whenever you get a closed bracket, okay, and in stack, if there is an open bracket matching it, then pop it. That's all. Very simple solution. Okay. So how do we write the transition function for this? The same thing, how will I write? So as I said, if I am in a state called as S, if I get an open bracket, it doesn't matter what is there inside the stack, I am going to push it. Correct? Similarly, the next is, if I am in a starting state, if I get a closed bracket and there is an open bracket inside the stack, then I am going to pop it. That's all. Very simple ones. Okay. So these are the delta in pictorial form and as a transition rule format. So for designing, in your mind you answer what is K? How many states we have? Only one. Right? And what are the alphabets? You have two alphabets, open and closed. What is tau? In stack, I am going to push only open bracket. Delta I have written already. What is the starting state? We have only one state. And what is the accepting state? We have only one state. Okay. Never forget to write them in the exam. Alright. They are important. So even if I skip explaining that, you have to write it in the exam. All that. Now let us see how it works for computations. Let us take the first computation like this. It should be accepted, correct? So let us see whether it will accept. Okay. So we start with the starting state. My input is this and nothing is there in the stack. So do I have a transition function for S open and anything in the stack? Yes, that's a push function. So it will be S, this one, and we are going to push the open bracket, correct? So S open bracket, as I said, this will tell, doesn't matter what is there in the stack, right? So open bracket is there, so you push it. So S closed bracket and open bracket twice, correct? All right. Now next, I have a closed bracket. So S closed bracket and open bracket. So you can see S closed bracket and open bracket, it says pop. So S, one closed bracket and one open bracket remains. So again it is a S closed and open which says pop. So after popping you are there at S, epsilon, epsilon. So it will be accepted because S is acceptance state, nothing in input and nothing is there in the stack. Okay. Let us take one more computation and see whether we can whether it rejects correctly. Okay. So for example, let us take this. So initially starting state and nothing is there in the stack. So I get an open bracket. So I'm going to push that. Correct? So no issues. Next, S closed bracket and open bracket. So I'm going to pop it. Now here I have a S closed bracket and epsilon. So you can see here for that we don't have any transition. So you are going to reject it, okay, because there is no transition for this. Since there is no transition, input will not be completely consumed, right? So that's why we are going to reject it. Okay, that's why we are going to reject it. All right. So again, I'll repeat. Only when you have epsilon here, no, it means empty stack or anything. Okay, empty stack or any content in the stack, doesn't matter. That doesn't mean that if I have specified something, this has to be there. It won't be anything. It has to be there. All right. Now I'll move to chat section. Can you tell me whether you understood this? You want explanation once more, or can I move ahead to the next problem? Have you understood this question? Okay. So let me move to the next one. Let me take the third question. It says, this is a palindrome, okay, WCWR, okay, where W belongs to AB star. This will not, you cannot design a PDA, okay, you cannot design a PDA for WWR. You cannot. This is even palindrome. You can design for this, I said you cannot design PDA, but we can design Turing machines, which is the next topic. Okay, next module or next topic. However, I can design a PDA for something like this, where you have in between a marker. This is an odd palindrome. Okay, so I can design PDA for odd palindrome, especially if I have a marker in between. So as you can see here, input has only A and B, right? So W is made up of A and B. WR is also made up of A and B, but in between, I have a marker called as C. So you can design PDA only for this question. You cannot design it for WWR, which means they'll be made up of only A's and B's, okay? For which again next topic we'll take, that is Turing machine. After a few classes, we'll see we can design it using Turing machine, okay? So what is the logic that we are going to apply? Now let us see some examples for that palindrome, okay? So ABCBA should be accepted. This is a palindrome. This is W. This is WR, W reversed. And in between I have a C marker. So this should be accepted. Okay. Should it accept only this? Of course it should accept this. Right? It can consist of A and B star. Should it accept a null string? Yes, it should accept a null string because it's a star. Correct? And what should be rejected? AB should be rejected because this is W, but this is not WR. So this should be rejected. Okay. It should also reject, let us say AB and B. They don't match at all. The lengths don't match. So this is W and this is not WR. So this should be rejected. So here for one symbol you can't push into the stack, and for one symbol you can't pop. Like previous two questions, whenever I got A, I pushed it. Whenever I got an open bracket, I pushed it in the previous two examples, right? The same logic cannot be applied here because W can have both A and B. So what we will do is, until you get a C marker, you are going to push, okay? Whether it is A or B, just push it till you get a marker called as C. And after you get a marker, then for every symbol here, if they match this, then you are going to pop it. Okay. For example, here B will match with this B, right? And A will match with this A. So you will be fine with that. So even in this case, when you pop, they'll match. But here you see, you would have pushed AB, but when you're popping, this A and this B will not match. Okay, I mean, we will write the PDA transition functions like that. So it should not match. So it should be rejected. I hope you understand how this question works. Okay. So let us start designing. So as I told you, what did I say? Until you get C. Let us start from the starting state. Okay. And can I make S itself as final state? No, because I have to get C. It's compulsory, right? So we said WC, WR. So I have to get a C. So in this question, I'm not going to make the starting state as the final state because C is compulsory. Okay. Even if nothing is there, because AB star you saw. So even if nothing is there for W and WR, C definitely has to be met with. Okay, so that's why I'll not make the starting symbol itself as the final status symbol. So what did I say we are going to do? If you get an A, it doesn't matter what is there in the stack, you are going to push it, right? Similarly, if you get B also, doesn't matter what is there in the stack, you are going to push it. And when you get this C, only after that your popping action will start. So that's why when you get a C, I am going to go to a final state. Okay. There is a possibility of me going to a final state, right? So, but when you get C, doesn't matter what is there, you will not do any action. So far you haven't seen this, isn't it? This means that if your input is C, it doesn't matter what is there in the stack. You are going to keep it unchanged. I had explained this in the first class when we discussed the PDA. What are the various types of transitions possible? So if you have forgotten, you can check that video. Okay. Sometimes we consume the symbol without making any changes to the stack. So this represents that. Okay. New one. So please remember. All right, once you pushed all the symbols, you also have seen C and you make no changes to stack. Now for this, if you have A and A, you have to pop it, right? And if you have B and B matching, you have to pop it. So if input is A and inside stack you have A, pop it. All right. If the input is B and in stack also you have B, pop it. Okay. So this is your delta. So how do we write delta here? So initial state is S. If you get A, doesn't matter what is there in the stack, you are going to push it. Similarly, initial state is B, doesn't matter what is there in the stack, you are going to push B, right? You are in the initial state, you get C, doesn't matter what is there in the stack. You are not going to take any action, you are only consuming the input, okay? And sorry, S. And if you are in, but you are, sorry, you are going to make a change of transition from S to F on C, correct? So you are at C, you are at S, you get C. Doesn't matter what is there in the stack. You make a transition to state called as F, and you make no changes to stack. Okay. Now you are in F, and if your input is A, stack symbol is also A, you are going to pop it. And if you are at F, and if your input is B and stack symbol is also B, you are going to pop it. Correct? Pop it. This is the same logic you used in data structure. You remember making use of a stack to find whether a given string is palindrome or not. Only difference is here we are using a C marker. Now let us take one or two computations and see whether we accept or reject. Okay. Let us take a computation for ABCBA. It should be accepted. So you start from the starting state. Your input is ABCBA and initially nothing is there in the stack. What is this called? In case you have forgotten, this is called as initial configuration, right? This is my initial configuration. What are we doing? We are doing a computation for a string called as ABCBA. Why I specified this is, in exam they might ask, design a PDA and show for some computation how it rejects or how it accepts. So they might give you the initial configuration or they may not give. They may give you freedom to choose anything and do it. Okay. So never forget, this is not the complete answer. Even writing computation is also not the complete answer. You have to design. Design, always remember, you have to tell what are all this. Okay. What are all this, you have to inform. Okay. You have to tell that. Is that clear? Some tuple I left. I don't know which one I left. Starting state, accepting state. Now, okay. Transition, delta. Delta. You have to tell what is all that. Okay. Now, do I have a transition for S, A and this? Yes. Right. So here is the transition which is push. So remaining input is BCBA. So I am going to push that first A. Okay. Push that first A. What about next? Do I have SBA? So SB, as I told, if I have epsilon here, it doesn't matter what it has, right? So SBA is SB. So push B. So you have consumed B, the remaining is CBA. So remember, when you push, this will be the top of the stack. Whatever you push later will come here. Always remember that. Okay? Don't write it as AB. When you push, it is tempting to write it as AB, but remember, this is what is pushed first, this is second. Whatever you push next has to come here. The stack grows like this. Okay? Now you have SC and doesn't matter whatever is there. Whenever you have S and C, what do? You consume this C, that's all. But you change the state to F, correct? Once you consume C, here, you move from state S to F. So F, B, A, and in stack you are making no changes. Now you have F, B, B, So you can see FBB is pop, correct? So you are left with FAA. Again for FAA also it is pop. So you are left with F epsilon and this will be accepted. Why this will be accepted? F is a final state. You consumed all the input and there is nothing inside the stack. Okay. Now let us write a computation to reject. Okay. So to reject, let us take ABC A, ABC A. Okay. So starting state ABC A and epsilon. So first you will push it. So what is left? BCA and you pushed A, right? Next you get B, so you push that also, correct? Till you get a C, we always push it. Again, remember what you push last should come towards the left end. Okay, representation is like that. Next you get, there is no comma here. Next you get a C, only change you make is change of the state, right? And you do not make any changes to stack or input, so they remain as it is. Now FAAB, for this we do not have a transition. Once you go to F, you have A on A or B on B. For this we have no transition, right? Since we have no transition for FA comma B in our design PDA, this particular configuration or this string is rejected. This string is rejected, right? There's one more example. Can I take 5 more minutes of your class or 3 minutes of your class? Did you understand this, whatever we solved now? Can you tell me whether you understood first? Tell me yes for whether you understood or not. I'm at a chat section. Did you understand that question? Yes. Can I take just 2 minutes extra? You can start putting the attendances. Okay. You can mark attendance and just listen to this one more question. I don't want to take one more class for this. Okay. Just give me 2-3 minutes. That's all. Let us solve a last question. The question is a power n, b power 2n. Okay. For n number of a's, you should have twice the number of b's in the string. Twice the number of the b's in the string. This is the question. Right? So for example, ABB should be accepted. AA4B should be accepted. What about AB? BAB. Here also we have twice B compared to A, but this is not correct because first A and then B. First A and then B. So this should be rejected. Similarly, this doesn't follow the rule, should be rejected. Okay. If I have epsilon, then it should be accepted because nothing should be accepted. Okay. I hope this is clear. So let us solve this question. So what is the logic we could apply here? We know only pushing and popping. So logic you can apply is for every A you see in the input. Okay. For every single A you see in input, you push 2 A's. Okay. Push 2 A's. You can do that. Alright. And then for every B you see in input, pop 1 A. Can you understand how it's working? It's beautiful, isn't it? See here. For every A, you saw 1 A, you push 2 A's into the stack. Next, for this B, you will pop 1 B, and for this B, you will pop 1 B. Alright? So, that's how we are going to design it. I'll give you a few questions as assignment. Later, you can think and design it yourself. Okay? So, taking the knowledge of all these 4 questions, you should be able to do it. So as I said, starting state I'll make it as a final state. Why? Because nothing also should be accepted. The next thing I told in the logic is for every A you see, doesn't matter what is there in the stack, you push 2A. correct? And on getting a B, I make a transition to final stage. Why? Because after B, I should not get A. So I'm keeping A towards the left. Okay. And for every B, if there is a inside the stack, I'm going to pop it. Fine. And once you come towards the B, once you saw one B, it's always popping, right? For every A, you pop it. Now let us see one computation to accept it and one to reject it. Okay. So let us take A and 4 Bs as my initial string. Nothing is there in the stack. So as I said, if you are in state S, right, and doesn't matter what is there in the stack, for a single A, I am going to push 2 A's and I will remain in state S itself. So S, one input is taken. Now in stack, I am going to push 2 A's. Correct? Push 2 A's. So it's the same thing, S and A. So it doesn't matter what is there in the stack. So for single A, which I consume, I'm going to push 2 A's into the stack. Now I have S and B, starting state, transition on B. What are we going to do? One symbol from stack. If it is A, we are going to pop it. So 3 inputs remain and 1 A is popped. So you have 3 A's remaining. Same concept will be carried ahead for all the remaining, isn't it? So for every B, you are going to pop 1 A. So ultimately you are, I made a mistake. Where was that? As soon as I get a B, I have to go to final stage, right? I have to go to final stage. So ultimately we are at F epsilon epsilon. Accepted. F is final state and these two. Similarly, just last 1 minute, we'll take a very small string to reject it. Let us just take BBB. Right? There is nothing for SB and epsilon. Correct? You can see here from starting state, S and B transition is there only if A is there in the stack. We don't have B, epsilon, anything. So this will be rejected. No transition, correct? So let us take S, A, B, B. Again, this should be rejected. Of course, for S and A, I have that is push, correct? So I'll be pushing 2 A's. Now, as you can see it unfolding, for S, B and A, I'll go to F and I'm left with B, B, A. And then again, F, B, A, I'll remain in F and this. And again, there will be no transition for this from F, correct? You can see here, once you are there in F, only transition you have written is B and A. For B and epsilon, there is no transition. So, you reject it.